Okay, folks. Announcements and plans. Number one. If you are planning to come tonight to help with the Conway STEAM, which stands for Science, Technology, Engineering, Arts, and Math night. Bring your goggles. Try to be at the Buzz Bolden Arena at 5 o'clock so that I can explain your activity. That way you can explain it to the kids. The activities are not overly complicated. One of them that we will be doing is going to be Alka-Seltzer rockets. One will be rose petal pH. One will be UV beads. One will be, can you taste the peppermint? And one will be marbled paper. So a lot of hands-on fun activities for individuals that will be there. If I have more than I need, I've got the American Chemical Society group that will be there doing slime. And then Dr. Dooley will be there with some activities as well. And so we can spread out. Do me a favor real quick and raise your hand if you're planning on coming. Because I know some people have backed out on me. 1, 2, 3, 4, 5, 6. I got more than enough activities. So, okay. Because originally there were 20 people coming. So, okay. I have more than enough activity. Yes. If at all possible. I know a couple of people are in lab until 5. And so they're going to be getting there right at 5:30. Or they're in a class until 5 and they're going to get there right at 5:30. I understand that. Yes. I will have a sign-in sheet, whether it's just a sheet of paper or whether I remember a sign-in sheet. Remember that it is worth 10 points. Second announcement. Even though I worked fairly diligently during the lab yesterday, I'm still working on the tests. I will have them graded this weekend, and I will have them posted this weekend. I'm posting grades because Monday is W deadline. Whether that's for my class or for another class, I want you to be aware of where you stand in class. But Monday is the W deadline for classes. So. Now the plan. Today, what I'm going to do is I'm going to pick up where I left off on Tuesday. On Tuesday, we performed some stoichiometry. And at the very end of Tuesday, I introduced the concept of percent yield. I am going to pick up with an example problem where we do some stoichiometry and ultimately we calculate percent yield. After that, I will move into different types of chemical reactions. Which brings me to labs. The lab you did yesterday is due on Tuesday. It's one per group. So if you are a group of 2, it's you and your partner's name. If you are a group of 3, it's you and your 2 partners' names. However it works. One per group, please. The lab we did prior to spring break is the material that I start to cover today. And so you will be able to start answering those questions. Now, the lab that we did prior to spring break, I will tell you exactly when it is due because I'll have a much better idea on Tuesday of next week, but it won't be due Tuesday. I'll have a much better idea of when it will be due after Tuesday or next week. And that lab is one per person and it will be turned in on active. I think that's all the announcements. Questions? Trying to keep up with everything. As I said, if you're coming to the event tonight, bring your goggles. Okay. Then we are going to get started into the information that I concluded with on Tuesday, which is performing stoichiometry with the one additional piece of determining the percent yield. So if you'll recall on Tuesday, I introduced this concept of stoichiometry. We performed a problem. I introduced the concept of limiting reactant. We identified which was the limiting reactant. I introduced the concept of theoretical yield. We identified what theoretical yield was, and then I had introduced this concept of percent yield. But that's as far as I got because we did not have time to calculate it. So today what we're going to be doing is we are going to be calculating percent yield. We're going to be determining the limiting reactant and the theoretical yield. This, folks, is similar to how it will appear on the test for this type of problem. Okay, so consider the reaction where 2 arsenic reacts with 6 sodium hydroxide to form 2 sodium arsenite and 3 hydrogens. What is the percent yield of hydrogen if 0.056 grams of hydrogen are produced from the reaction of 9.43 grams of arsenic with 2.6 grams of sodium hydroxide? And I gave you the molar masses of the various compounds. Okay. So first things first, What is it I'm working on? I want to know the percent yield of hydrogen. And I give you 0.056 grams of hydrogen. That 0.056 grams of hydrogen, folks, that is your actual yield. In other words, unless we're in a laboratory, you will have to be given the actual yield. Unless we're in the lab, you have to be given the actual yield, because actual yield is determined through experimentation. So when we're talking about the percent yield is going to be the actual yield divided by the theoretical yield times 100. Again, unless you're in the laboratory, the actual yield has to be given to you. So that is that 0.056 grams of hydrogen. What you will be responsible for is calculating the theoretical yield. In this particular case, I know that it is a limiting reactant problem because I am given a quantity of both reactants. That is your telltale sign that it is going to be a limiting reactant problem. Therefore, I need to convert the arsenic into hydrogen, and I need to convert the sodium hydroxide into hydrogen. So let's convert the arsenic into hydrogen. I want to convert 9.43 grams of arsenic into grams of hydrogen. The very first thing that jumps out at me is that arsenic and hydrogen have different formulas. That means I'm going to need a mole to mole ratio, which is going to come from the balanced chemical equation. According to the balanced chemical equation, 2 moles of arsenic is in a ratio with 3 moles of hydrogen. The next thing that I notice is my unit of arsenic. My unit of arsenic is grams. Anytime I see grams, that means you're going to need the molar mass. Well, I gave you the molar mass. That is 74.92 grams of arsenic is equal to 1 mole of arsenic. The third thing is I notice that I have grams of hydrogen. Again, grams tells me that I'm going to use the molar mass. In this case, 2.016 grams of hydrogen is equal to 1 mole of hydrogen. That is terrible. Okay. Now that I've broken everything down, I'm ready to do this part of the problem. So 9.43 grams of arsenic. My first conversion factor needs grams of arsenic. That is going to be the 74.92 grams of arsenic is equal to 1 mole of arsenic. The grams of arsenic is going to go in the denominator so that the unit and the substance will cancel out, leaving me moles of arsenic. Next, I'm going to use the mole-to-mole ratio to convert from moles of arsenic to moles of hydrogen. According to the balanced chemical equation, 2 moles of arsenic produces 3 moles of hydrogen. Again, I put the arsenic in the denominator so that it would cancel out, leaving moles of hydrogen. But I need the mass of hydrogen, so I'm going to use the molar mass of hydrogen to convert it into moles of hydrogen, or into mass of hydrogen. So 2.016 grams of hydrogen is 1 mole of hydrogen. I place the mole portion in the denominator so that the unit and the substance will cancel, leaving me grams of hydrogen. Keying this into the calculator, you get 0.381 grams of hydrogen. That is the amount that the arsenic can afford me. But this is a limiting reactant problem. It's a limiting reactant problem because I was given a quantity of both reactants. So I cannot assume that arsenic was the limiting factor. I have to also do the conversion for sodium hydroxide. Which was 2.6 grams of sodium hydroxide. And I need to convert that into grams of hydrogen. We can go through the same process, and you're going to see you need the mole-to-mole ratio, which is 6 moles of sodium hydroxide to 3 moles of hydrogen. You will see that you need the molar mass of sodium hydroxide, and that is 39.998. Is equal to 1 mole of sodium hydroxide. And again, you're going to need the molar mass of the hydrogen, which is 2.016 grams of hydrogen is equal to 1 mole of hydrogen. Once you have all that data, then you can do your conversion. So 2.6 grams of sodium hydroxide your first conversion factor is going to have grams of sodium hydroxide. So that is going to be the 39.998 grams of sodium hydroxide is 1 mole of sodium hydroxide. The grams are going to go in the denominator so that the unit and the substance will cancel, leaving moles of sodium hydroxide. Then we use the mole-to-mole ratio. 6 moles of sodium hydroxide is to 3 moles of hydrogen. The moles of sodium hydroxide are placed in the denominator so that the unit and the substance will cancel, leaving moles of hydrogen. Now we can use the molar mass of hydrogen. Of that molar mass, the moles were placed in the denominator so that they would cancel. And when you complete this calculation, you get a value of 0.0655 grams of hydrogen. Looking at the grams of hydrogen that can be produced from the arsenic compared to the grams of hydrogen that can be produced from the sodium hydroxide, you will see that the grams of hydrogen that can be produced from the sodium hydroxide is in the lower quantity. Therefore, this is your theoretical yield. And it came from the limiting reactant. Question. Now that I know my theoretical yield, I can go back up to this percent yield and finish the problem. Because I now have the value I need to divide by to get the percent yield. And you get an 85.5% yield for hydrogen. So once again, just looking at this problem. I was asked for the percent yield. Percent yield is a formula. It is the actual yield divided by the theoretical yield times 100. Except in the laboratory, you will always have to be given the actual yield. Because the actual yield is determined through experimentation. That is why the 0.056 grams of hydrogen was my actual yield. What I had to do is I had to determine what the theoretical yield was. And unfortunately, I had starting quantities for both reactants. Because I had starting quantities for both reactants, I had to perform 2 stoichiometric calculations. I had to convert each reactant into the desired product. So I converted the arsenic into the desired product. And then I converted the sodium hydroxide into the desired product. I then looked at the mass that each of those calculations afforded. The one that was in the lowest quantity was my theoretical yield. And that is what I then placed back into that percent yield calculation in order to finish it. And the theoretical yield always comes from the limiting reactant. The limiting reactant being the reactant that is going to run out first. Questions? Lots of math. Okay. We're going to move back away from math for a couple of days. And dive deeper into understanding the chemistry. Specifically, we're going to dive deeper into aqueous reactions. Aqueous reactions are reactions that occur in water. And we're going to focus the majority of our time on 3 types of aqueous reactions. The first type of aqueous reaction we will discuss is going to be the precipitation reaction. If you will recall from the laboratory prior to spring break, I described a precipitate or a precipitation reaction as a reaction that formed a solid as one of its products. The second type of reaction that we're going to get into is going to be an acid-base neutralization reaction. As the name would suggest, acid, base, meaning we're going to react an acid with a base. Now, the other part of that name is a neutralization, meaning we're going to form water and a salt. The third type of reaction that we're going to discuss are redox reactions. Redox reactions involve transfer of electrons. Now, with precipitation reactions and acid-base neutralization reactions, we're going to actually describe them using 3 different chemical equations. The first chemical equation is going to be the balanced chemical reaction. We already have experience with balancing a chemical reaction. But what we're going to do is, as part of this process, is we're not only going to learn to balance the reaction, which we've done, but we are going to learn how to predict the products. So that is where we're diving deeper into the chemistry. So we're going to learn to predict the products of the precipitation and acid-base neutralization reactions. Now, the balanced chemical equation is probably the least informative of the chemical reactions. It doesn't delve deep into what is going on in solution. To delve into what is going on in solution, we are going to take that balanced chemical equation and we're going to convert it into a complete ionic reaction. To take a balanced chemical equation and convert it into a complete ionic reaction, we have to be able to separate strong electrolytes into their components. Probably out of our chemical reactions, the complete ionic reaction is the most informative as to what everything looks like in solution. But we are going to take it one step further, and we're going to get to the net ionic reaction. The net ionic reaction explains what undergoes a change. What actually happens in the reaction? What undergoes a change? What undergoes a chemical change? To get from the complete ionic reaction to the net ionic reaction, we're going to remove our spectators. And a spectator is a lot like a sports spectator. For the most part, they come into the game and walk out of the game the same. In our chemical reaction, the spectator ions are going to walk into the game and walk out of the game the same. Now, there are a lot of terms up here that we're going to have to delve into in order to be able to do this. The first thing that we're going to have to do is we're going to have to delve into the solubility rules, because the solubility rules are going to determine who forms a precipitant and who doesn't. You'll be grateful because I give you the solubility rules on a test. You just have to know how to interpret them. At least I hope you're grateful. A little bit less to memorize. We're going to have to be able to determine who is an acid and who is a base. To know whether we've got an acid-base neutralization reaction. So we're going to have to delve into that. The next thing we're going to have to delve into is this definition of an electrolyte. And when we get into electrolytes, we're going to be able to should be able to describe them as strong electrolytes, weak electrolytes, or non-electrolytes. This definition depends upon how well they conduct electricity. A strong electrolyte conducts electricity really, really well. A weak electrolyte, light a bulb, but not very well. And a non-electrolyte doesn't conduct electricity. So again, we're going to have to get into all of these definitions in order to be able to come back to these chemical reactions. And that is what we're going to do now. Okay. First of all, a precipitation reaction is a chemical reaction that produces a solid as one of the products. We use the solubility rules to determine whether an ionic compound is a solid or aqueous. In water. Okay. I capitalized one word. Ionic. How do you distinguish an ionic compound from a covalent compound? What am I looking for in an ionic compound? I'm looking for a cation, which means in all cases except ammonium, I'm looking for a metal. So in other words, these solubility rules, all they apply to are the ionic compounds. So we're going to describe the solubility rule, and then which means if I say it's soluble, it means that it is aqueous. And then I'll explain the few exceptions associated with that rule. And if it's an exception, that means that it is a solid in water. Okay, rule number one of the two most important rules is group 1 and ammonium compounds are soluble. There are no exceptions. So if I see sodium chloride, because it contains group 1, it's soluble. If I see rubidium nitrate, because it contains group 1, it's soluble. If I see ammonium carbonate, because it contains ammonium, it's soluble. There are no exceptions to that rule. Rule 2, nitrates, acetates, perchlorates, those are soluble. No exceptions. Rule number 3. Chlorides, bromides, iodides, they are soluble, except if the cation is silver, lead 2+, or mercury 2+. The next rule, sulfates are soluble, except silver plus, lead 2+, mercury 2+, calcium, strontium, and barium. Insoluble. If we describe something as insoluble, it means that it forms a solid. And if it is an exception to the rule, then that means it is aqueous. Oxides and hydroxides tend to be insoluble unless the cation is group 1 metal, ammonium, and then to some degree, calcium, strontium, and barium. These are slightly soluble. For our purpose, all other anions tend to be insoluble unless the cation is a group 1 metal or ammonium. Folks, other than rule number 1, Notice that the rules are about the anions and the exceptions are about the cation. If you pay attention to rule number 1, then these exceptions are already dealt with. That's why I said rule 1 and rule 2 are the most important. They're the first things you do, is you identify whether something is soluble or insoluble based off of rule 1 and rule 2. And yes, I tried to write things up so that you could see patterns. So, the last thing I will say about the solubility rules. Start at the top and work your way down. Once you've assigned something as soluble or insoluble, once you've assigned it based off of a top rule, you don't have to worry about that compound again. Let's look at a couple of examples. What would be the state of matter of lead 2 nitrate? Rule 1 does not apply, but rule 2 does. Rule 2 says nitrates, acetates, perchlorates, they're soluble. Because this contains nitrate, it means that this compound is soluble. But we cannot say the same thing about PbCl2. Rule 1 is not applicable. Rule 2 is not applicable. So we have to pay attention to rule 3, which deals with the halogens. And in this case, the lead is an exception to the halogen rule. Therefore, this is a solid. Let's talk about FeOH3, iron 3 hydroxide. Since the metal is not rule 1, that means I need to pay attention to the anion. So I'm looking at the hydroxide rule. The oxide hydroxide rule is that it is insoluble. The question is that an exception? Since iron is not one of the exceptions, that means that this is going to be insoluble. We will get a lot more practice with the solubility rules. when we start dealing with complete net ionic equations. The next thing, though, I want to talk about is acid-base strength. First of all, an acid is going to be a proton donor. A proton being represented with an H plus, which we have discussed previously. Now, we can take an acid and divide it into a strong acid or a weak acid. And yes, you are going to need to be able to differentiate, and you will need to memorize. There are 6 strong acids that you must know. They are HCl, HBr, HI, HNO3, H2SO4, and HClO4. For the weak acid, it's going to be any other compound whose formula starts with a hydrogen or has the COOH functional group. This COOH group, by the way, folks, many of you have seen it. It is called a carboxylic acid. Now, for our bases, we are going to use the Arrhenius definition of a base for what we will be doing. Which means that it is a hydroxide donor. The strong bases, you actually don't have to memorize. They are your soluble, meaning aqueous, hydroxides. So you don't actually have to memorize that. Weak bases are going to be your insoluble, oxides and hydroxides. And compounds that contain an amine functional group. An amine is going to have NH, where the number of hydrogens can equal 0, 1, 2, or 3. Anybody ever hear of an amino acid? It has an amine and it has a carboxylic acid. That's how it got its name. So, okay. So, the last set of definitions that we need to go over is this concept of an electrolyte. An electrolyte is a substance that dissociates into cations and anions in our case in water. One classification is that it can be a strong electrolyte, which means that you're going to have complete dissociation. Into ions. Now, your strong electrolytes are going to be your aqueous ionic compounds, and your strong acids. Technically, your strong bases as well, but they're aqueous ionic compounds too. A weak electrolyte only has a partial dissociation into ions. Your weak electrolytes are going to be your solid ionic compounds. Your weak acids and your weak bases. Your non-electrolytes does not dissociate. And this falls under is everything else. Lots of definitions today. But you can't do anything until you get all these definitions down. So, why did we go through this? Well, we had to stop and deal with the solubility rules because without the solubility rules, you don't know who's an aqueous ionic compound and who's a solid ionic compound. We had to stop and figure out who are our strong acids, weak bases, because without that, we don't know who is a strong acid, weak base. And if you can't classify compounds into those categories, then you can't classify compounds as strong electrolyte, a weak electrolyte, or a non-electrolyte. And if you can't classify a compound as a strong electrolyte, weak electrolyte, or a non-electrolyte, then you can't decide what to do with it when you go from the balanced reaction to the complete ionic reaction. Which is what our topic for Tuesday will be. Is we will actually bring your laboratories, because I may actually use a couple of equations out of the lab in going over this topic. But what we will be doing on Tuesday is number one, we will learn to predict the product of precipitation reactions and acid-base neutralization reactions. Number two, we will determine how to go from the balanced chemical equation to the complete ionic equation. And once you get to the complete ionic, the net is easy. So bring your labs, because I'll probably do at least a couple of examples directly from your lab. And what the lab I'm talking about, by the way, is the lab we did prior to spring break. few of you tonight. Don't forget goggles if you're coming. Otherwise, I will see you on Tuesday, and I will get your grades done.